This program is brought to you by Stanford University. Please visit us at stanford.edu.
This presentation is delivered by the Stanford Center for Professional Development, providing graduate-level education to working professionals, online, on campus, and on-site. For more information, please visit study.stanford.edu.
Norm Jouppi is here from Hewlett-Packard, and he'll be talking about high-performance microprocessors. He has a PhD from Stanford in electrical engineering. He worked under Hennessy, who I'm sure all of you know, and was an original architect and designer of the MIPS processor before it became a company while it was Stanford Research. Then he went and worked at DEC and was a principal architect and lead designer for different processors there. And now he is currently working at HP Labs as a fellow and director of the Advanced Architecture Lab. And the talk he's giving today is actually an updated version of a Micro 2005 keynote speech. So just to let you know that that's where some of the content came from, and it's been updated for the current times. So please welcome Norm Jouppi.
Thanks, Eileen. So is my mic okay?
Yes.
Okay, great. Okay, so let me give you a brief overview of the talk. First, I'm going to be talking, I've got evolution in the title, so why and when of evolution. Some environmental constraints that shape that evolution. What is called the Powerwall these days. Some things that are important about power from the transistor to the data center that we're working on. If I have time, I'm going to talk about the evolution of computer architecture ideas, which is kind of my own pet theory, and then wrap up. So if you have any point of information questions, keeping in mind the interactive desired nature of the lecture, just ask me. If you've got longer questions, maybe we can save them for the end. Okay, so anytime I give a talk about my own thinking, I have this disclaimer. So these views are mine, not necessarily those of HP. And I'm reminded of a saying of Samuel Goldwyn, who was one of the founders of MGM Studios. There's about 30 quotes kind of in this flavor. This one is, never make forecasts, especially about the future. So I'm going to disregard that advice because it's more fun. So why evolution? Well, evolution is a very efficient way of building new things. So it does a lot of reuse and recycling, a minimum of new stuff. And it's much easier than revolution. If you think about evolution in terms of biology, you can categorize evolution into eras and periods. The age of the dinosaurs being right here, my middle son's favorite age. And they're characterized by different characteristics of biology. So technology is a lot like that. There's usually evolution and not revolution, although every once in a while there is a revolution. Many revolutionary technologies have had a bad history. So in the late 70s, there was this thing called bubble memories with magnetic domains. They didn't really go anywhere. There was Josephson junctions. That was kind of a very long gestation period. It didn't go anywhere. Gallium arsenide for digital logic, anything but Ethernet. In general, there's a lot of pressure to be evolutionary instead of revolutionary. And what's been the key thing driving this evolution in the industry? Well, it's really been Moore's law. So I'm sure you're all familiar with that. It was originally presented in 1965 when he had only about 4 data points. And originally he said it was going to be a doubling every year, but it really works out closer to be something like this 1.59 for the base. It was elaborated on by Dennard of IBM in 1974, which was classical scaling theory. And so classical scaling theory said with every feature size scaling of n, you'd get order n squared transistors, and they'd run order n times faster. There's a lot of other details in the scaling theory about what would happen to gate oxides, supply voltages, and all that kind of stuff, but we're just going to focus on those two things today. And then Moore subsequently proposed his design law and his fab law, and we'll be mentioning that in a little bit. Okay. Something that I've come up with in terms of categorizing the evolution of the industry is microprocessor efficiency errors. And so if you just take Moore's law kind of at the base, level with Dennard's elaboration, you should get, with a feature size scaling of n, order n squared transistors and a speedup of n, so an overall improvement of n cubed in computational capability. So just like most things that are physical phenomena, there's some saturation involved. Gordon Moore, another one of his quotes, is no exponential is forever. But even given the exponential driving of transistors and speeds, we're seeing a saturation in computer performance, single core performance. So my position is that originally we had an n cubed era, then there was an n squared era, an n to the 1 era, and then luckily we didn't get this far. And I'll be explaining that in the next couple of slides. So in the n cubed era, we were getting a factor of n from device speed and n squared from transistor count. And I categorize this as roughly being from the 4004 to the 386 generations. I'm using the Intel processors here just because people are most familiar with those technologies. But it applied to other manufacturers' processors as well. What did we see in that era? Well, we saw the expansion of data path widths from 4 bits to 32 bits. We saw implementation of basic pipelining. There was hardware support for complex operations, the 386 math coprocessor, like floating point multiply. They even added more complex things, but we won't go there. Memory range and virtual memory was greatly, the memory range was greatly expanded and virtual memory was added. So it's hard to measure performance in this era. Some people, when they plotted out graphs of performance over this range, come up with a not too much increase in performance because they basically just use MIPS, and MIPS they basically tie to the clock frequency. And the clock frequency, remember, was only going as order n, okay, roughly. So what's a more interesting question would be something like how many 4-bit ops in a 4004 are required to generate a 64-bit floating point multiply result to the IEEE standard. So this is the audience participation time. So how many people think it's less than 300? Raise your hand. Okay. Less than 1,000? Okay. Well, you guys are much better than the micro keynote, and you're not even in the architecture community, so I'm very proud of you. It's actually more than 1,500. And so this is something that's not factored in when you just compare the clock rate of the 4004 to the clock rate of the 386. Okay, the n squared era, what I think of it is roughly from the 486 through the Pentium 3-4 generation, kind of ending at the 3. We saw a factor of n from device speed, but we were only getting a factor of n from the n squared transistors. And why was this happening? Well, if you look at that era, we started having on-chip caches, and they kept getting bigger and bigger. And it's fairly well known that the miss rate basically halves as you quadruple the cache size. So there we're kind of getting the kind of square root. We get n squared transistors in, and we're only getting n improvement. Similarly, with superscalar issue, we saw an increase to 4-way issue machines. Maybe you'd get a 2x performance increase on a good day from that. Depends how deeply you were pipeline. Pipelining, you get diminishing returns. We saw a huge number of pipe stages in the Pentium 4 generation. Okay, so the N era, which actually wasn't very economically viable, you would be getting a factor of n from device frequency, but basically nothing from the additional transistors. And this basically covers a lot of academic proposals for very wide issue machines, like 8-issue machines. And there was an 8-issue machine being designed inside Digital Equipment Corporation and then later acquired by Compaq called EV8, which was the 4th generation alpha. And so the problem with the very wide issue machine was that it was little help to many applications because they didn't have that much instruction level parallelism. And it needed simultaneous multithreading, so it needed to be running multiple threads to justify that issue with. The problem was that basically the structures in EV8 were so large that they were inherently slower in terms of fan-out of 4 gate delays than the previous generation. So for example, the load store queue in EV8 was bigger than the entire processor on the same order of EV6. So that's a big problem. When you do that, a lot of the structure sizes, the structures slow down. You've got very long global wires to communicate from one unit to another. And the time to market can increase dramatically, in some cases to infinity. So let's look at environmental constraints that shape evolution for a little bit. There are several categories. First, we've got technology scaling things like economics, devices, and voltage scaling. And then we've got system-level constraints like power. So one of the other laws that Gordon Moore came up with was his fab law. And he said this about 15 years after his original law, I believe, that the fab cost basically scales as roughly 1 over the feature size. And today, a new 65 nanometer full-size fab costs more than $2 billion. Depending on who you're talking to and what article and stuff, it can be anywhere from $4 to $5 billion. There's a lot of, you can get a 60 nanometer fab for less than that if you reuse an existing fab that was designed to be upgradable. And so few companies can afford them by themselves. So we've been seeing a lot of fabless startups, a lot of fab partnerships, and large foundries being successful. But as far as the economic driver behind all this, the number of transistors scales is 1 over the feature size squared. And so each transistor is still getting cheaper, even though we're paying an order n more as we scale down. And the transistors are still getting faster. So we're still getting a factor of n squared economically. The other law that Gordon Moore had was the design law. So here he said that the number of designers goes roughly as 1 over the feature size. And just some recent check of this, the 4004 had 3 designers and was a 10 micron technology. And 90 nanometer microprocessors, of course, it's very, very confidential exactly how many people are working on one. But when you include, doing all the test analysis, all that other stuff, it's easily 300 designers. So that still seems to be holding. So the implication there is as we scale technologies, the design cost becomes very large. And so we've seen a consolidation in the number of viable microprocessors. Of course, even with the fab cost, that's been helping too. And there's a lot of push to reuse the cores. And so have small derivatives of previous cores to make new cores, because it's too much work to design them from scratch. This was pretty successful until just recently in deep submicron technologies. There's a lot of changes because the technology isn't scaling so ideally anymore, and so shrinking and tweaking is more difficult. Okay, in terms of devices, transistors have historically gotten faster according to the feature size, but the recent thing that's been happening is they've been getting much leakier because the gate oxides that we've been seeing have been only several atoms thick. So there's been some proposals to fix this, like high K gate dielectrics, and the industry thought that they were in pretty good shape a couple years ago, but there's been reliability issues and other things with that. So that's still kind of in progress, working on that. And we've also had a lot of channel leakage from one side of the transistor to the other. So eventually, it looks like we'll have to go to more complex geometries where we have 2 gates, basically, closing off the device from both sides. Yeah.
How close are we to running into fundamental limits like the size of atoms and the number of electrons in the gate?
Well, you'll see some people talking about that. I mean, it's the leakage. Oh, sorry. How late? Yeah. How close are we running into the atom limit? Well, in terms of the gate leakage, that's definitely the issue because there's tunneling through the gate when you only have like 4 atoms. But other things, once you fix the gate dielectric, I'm not too worried about it. So other people say we should have no problem going down to 20 nanometers. Most people are reasonably comfortable with the transistors. The interconnect might be more of an issue. So net result of all this is that even CMOS has significant static power. And the power is roughly proportional to the number of transistors that are powered on. And it's approaching even the dynamic power. The power of actually doing the useful work switching the transistors. The bad thing about this is that static power increases with chip temperature. And so, this is a case where positive feedback is bad, because as the device gets warmer, it leaks more, dissipates more power, gets hotter, leaks more, etc. And so you get kind of this thermal runaway that you have to avoid. Also, reliability of very small structures is an increasing problem, and high thermals are a problem for that too. So what about voltage scaling? Well, high-performance MOS started out with 12-volt power supplies, and the maximum voltage has been scaling roughly as the square root of the feature size. And so power, the simple equation is CV squared F. It's a square dependence on the voltage. And the speed does go down with lower voltage. That's one of the trade-offs, but it's still increasing as the feature size. So current high-performance microprocessors have 1.1 volt supplies, more or less. And that's reduced the power by 2 orders of magnitude in the last 24 years. So how much further can we ride that wave? Well, the problem is beyond a certain voltage, transistors don't turn off. And the ITRS roadmap projects a minimum voltage of 0.7 volts in 2018. And that's limited by threshold voltage variation, especially as you get to these, it's not kind of like a brick wall with a number of atoms. It's more of a gradual kind of thing that's getting worse and worse. So one of the things is there's more threshold voltage variation as things get smaller, because you're dealing with smaller numbers. But high-performance microprocessors are already at 1.1 volts, and so we've only got a factor of 2.5 reduction left in the next 14 years. So it's almost as if the voltage scaling goes away, the benefits of it. So that's kind of the bottom up. From the top down, if you look at the per chip power envelope, it's nearing air cooling limits. Okay, so we've had some chips around 100 watts. I designed one chip 115 watts. And the problem is that now we're seeing a lot of consolidation and blade systems and data centers. And so with one U server, 1.75 inch in a 19-inch rack, and also blades plugging into a chassis, there's very little room left for the heatsink. And basically, when you don't have a lot of room for the heatsink, it increases the thermal resistance that you can get, and that basically increases the temperature for given power dissipation. The other thing is that the cost of the power in and the heat out over several years can equal the original system cost, and it becomes a first-class design constraint. So this is the trends that Checker Borkar of Intel presented at a keynote in 2001, showing that if we basically just continue what we were doing design-wise during the era when we had voltage scaling and try to continue that out into the future when we don't have voltage scaling, things will get really crazy really quickly, so like 10,000 watts per chip. So obviously something had to change right here. Okay, so just to talk about the Powerwall a little bit, I'm going to try to put it in perspective. So some of you probably heard about the memory wall. I think of the memory wall as kind of like this fence here. There's been a lot of talk about it, but and if you're a cow, it's a significant barrier. But people are smarter. We can go up to it. We can climb over it. There's a lot of techniques you have to do. It requires some work, but it's okay. It's unpleasant sometimes. The Powerwall I think of as more like this. So things are pretty steep. You're going uphill when you get to it, and then things just go vertical. And there's no place to grab onto. So what are some ways that people have tried to get around or push out the Powerwall? Well, one general technique is what I call the Ben Franklin waste not, want not for circuits, where people have put in a lot of clock gating, low power circuit techniques, things like that, SOI. We've basically implemented a lot of, pretty much all of those things already. There's also power efficient microarchitecture, and we've seen that in the latest Intel Core announcements, where they go from a heavily pipelined design which uses more power to something with a lower clock frequency, more parallelism in units. This was something pointed out by Broderson at Berkeley, probably almost like a decade and a half or 2 decades ago, that if you went to more parallel units and ran them slower, you could save power. But there's only so much you can do by saving power. At some point, you're actually going to have to burn power. And what's the best way to burn the power? The only thing that I think is available at this point is what I call the single-threaded versus throughput trade-off. And if you go back to that saturation diagram that I had earlier, you think about the n cubed year or the n squared year. You know, when you go farther out on the curve, you're using a lot of transistors. They're all leaking, but you're not getting that much benefit from them. So if you want to have efficient computation, you have to get back towards the n cubed year. So thus, I think we'll see a trend towards simpler processors with narrower issue width, shallower pipelines, and more in-order processors or smaller out-of-order windows. And in fact, we've been seeing this since about the last year or two. It's kind of a back to the future scenario for architecture design in terms of microarchitecture. Now the problem is this: when you do these things, it gives you lower single-thread performance, and single-thread performance is very important for a lot of users. You know, a lot of applications for a desktop or a laptop. So you can't simplify the cores too quickly, or your competitors are going to get the market share. And the trade-offs on what to eliminate are not always obvious. So I'm just going to deal with 2 of them here, speculation and multithreading. Speculation in hardware, I mean things like branch prediction. So is speculation uniformly bad? Well, no. Imagine you execute down the wrong path. That would waste power. But what happens if you just stall every time you get to a branch? Besides being bad for performance, you're going to have all those transistors just sitting there leaking. So that hurts both performance and power. So predicting a branch can actually save power as long as your branch predictor isn't, you know, this huge million transistor thing. So the current amount of speculation seems excessive, but it seems like speculation is important even going forward in these smaller cores. The same thing can be said about multithreading. So multithreading and simultaneous multithreading, that's what SMT is for, is where you can be issuing instructions from different threads at the same time in the same cycle. That increases power efficiency, but the wide issue is still power inefficient for the reasons I was talking about earlier in the EV8 kind of design. But multithreading is useful even in simple machines, especially when you don't have these huge out-of-order windows to try to hide memory latency. During cache misses, transistors are still going to be leaking. So if you can execute some other thread in the meantime, that basically makes good use out of that leakage power. But you might not only need 2 or 3 threads, and you might not need to issue instructions for multiple threads in the same cycle, like the simultaneous multi-threaded machines. So just to recap possible future evolution in terms of the power equation, I think we're going to be seeing a power basically roughly constant going forward, and it'd be lower, lower would be even better due to system constraints. We see the voltage is roughly constant over the next 14 years. Clock frequency, I believe it's going to be not scaling with device speed. So what that means is as you get increases in device speed, you'll be scaling back the number of pipe stages at the same rate. So moving from 30 pipe stages at 90 nanometers to 10 stages at 30 nanometers. The big thing, though, is that the capacitance, the area, needs to be repartitioned for higher system performance and power efficiency. So looking at the number of cores per die, I think it makes sense to scale the processor complexity roughly as 1 over the feature size. And this is going to be rough here because, again, of the design reuse cost, right? So you probably want to use a core for several fab generations, and so it's not going to be kind of a continuous curve where you ramp down the number of transistors, but it's going to be steps. This would basically take us from 1 core at 90 nanometers to 27 per die at 30 nanometers. And this 27 per die, you could implement things like the 46 generation, which was a dual issue pipeline machine. Now, I heard at the Intel Developer Forum today in San Francisco, the Intel CTO was talking about perhaps even 80 cores per die by 2011, but they'd have to be very simple cores. So it's a question of how simple can you go. Because of multi-threading, the number of threads per socket is going to increase even more than this. So, we've moved from the clock frequency wars now to the core wars. But can we, as users, efficiently use that many cores and that many threads? Well, I'm an optimist, so my answer is yes, maybe with a time lag. But I think we're on the cusp of a golden age of parallel programming. And in this golden age, every major application is going to become parallel because necessity is the mother of invention. Now, how can we make use of many processors effectively? Well, a lot of applications are already highly parallel, right? So Google, serving queries on the web, computational fluid dynamics, TPCC, but other applications are very hard to parallelize. And parallel programming is a hard and costly problem that people have been working literally for decades on. And Sherry Pancake, who's a professor, has some interesting guidelines where she says that basically to develop parallel code is about 10 times more expensive than serial code, and if you're developing massively parallel code, it's 100 times more expensive than serial code. Where massively parallel might be something like IBM Blue Gene L, which has now over 131,000 processors. So maybe there's a square root dependence in number of programmers with number of processors or something like that. But it's not good. We'd like something more like linear. Other people have been proposing doing large amounts of speculation in software, but then you just kind of push the power inefficiency up a level. I think the really key thing in determining what works is going to be power efficiency. And so if you're executing a bunch of threads speculatively and you have to throw away that work, then it's just like doing too aggressive branch prediction or out of order execution in the core. It's not a good thing to do in terms of power efficiency. So this is a slide I've added since the micro keynote based on the feedback that everyone always gives me from the last slide, which is, what are you thinking? It's a hard problem. Why didn't it happen a decade ago when people first were really looking at this in earnest, for example, at Stanford with the Dash and Flash systems? Well, if you look at what was going on in the 90s, we basically had at most one processor or core per chip. And so if you wanted to create a shared memory multiprocessor, it took basically expensive glue chips, ASICs, to connect them together. So if you look at the system with one chip and a system with several chips, because of the complex ASICs to connect them together, you already had, if you're running a serial application on one of these processors on a complex machine, you already had worse performance for a given amount of money. So first you take this big hit. And then if you get any parallel speed up less than linear, that made it even worse in terms of efficiency, cost, performance efficiency. And it was programmed by gurus, so there was many grad student hours of optimization going into the Splash 2 benchmarks, for example. So what's different now than in the 1990s? Well, in the CMP era that we're in now, the chip multiprocessor era, your microprocessor will come with N processors whether you like it or not. Okay. And given a fixed cost, you're going to pay the same amount for that microprocessor whether it had one core or N cores, because they'll all have N cores. Any speed up is going to look good. So if you get a speed up of 2 from having 8 cores and you have 8 cores on your laptop, then hey, that's not so bad. The big issue though is getting to the programming cost. So there's still a lot of work needed on tools for the masses of future parallel programmers that are going to be needed. So right now, kind of in keeping with the deep dive, I'm going to talk a little bit about architecture research issues that are interesting in terms of this environment. So there's a lot of issues. How to wire up chip multiprocessors internally, the cores in a chip multiprocessor. What kind of memory hierarchy should it use? Should it be kind of hierarchical? Basically, any kind of hierarchical structure will have more difficulties in programming because then your programmers have to think about where the location is of the core on the chip multiprocessor for more effective sharing. And that will drive up the programming cost and the difficulty. So you'd like kind of a flat interconnection network, but that might not be possible technologically. how to build the cores. I'm going to talk in more detail about two of these three ideas because I've been involved in those. First is heterogeneous CMP design. So having different kinds of processors making up the chip multiprocessor. Some big ones, some small ones, and having kind of transparent migration in software. Conjoint core CMPs. And I'm not going to have a separate slide on this, but I think what's also very interesting is having stacked die. There's been some interesting papers recently, both on the technology side and the architecture side. The upcoming ASPLOS conference, there's a paper on stacking DRAM underneath basically the processor chip. And so if the DRAM is low enough power and the processor chip is up against the heatsink, and you have low resistance connections through the DRAM chip, it can basically help you with the memory wall issue and also reduce the system power because you're not going off chip. The big thing again is how to program, and there's work going on at Stanford and other universities and industry about transactional memory systems. And then I'm going to talk a bit about power. Now this is kind of at the micro level. There's also a bunch of system level problems which are very interesting. You know, as the computers keep getting smaller, you know, we're down from like 1U to, you know, several processors on a blade. We've got a lot more things to interconnect in a data center. So cluster interconnects are a problem. You know, managing all these different system images is a problem. Availability, if you're trying to run a large problem on a machine with 131,000 processors, you know, what happens when one of them goes bad? One of them will go bad pretty frequently compared to the job size of some of those machines. Security, things like that. Those are beyond the scope of this talk, but all very interesting problems. Increasingly what we're seeing is that hardware-software trade-offs kind of that are covered by the ASPLOS conference, which is going to be held in San Jose in a month, are increasingly important. So it's not just hardware can do it or software can do it, but teamwork is required. And so that's one reason why ASPLOS is moving to an annual schedule. So I'm going to talk about a few things that we're working on at HP, some in partnership with academic partners. The first is heterogeneous chip multiprocessors, and there's an overview article on it in the November 2005 Computer Magazine by Rakesh Kumar et al. And companies like to call the same thing different things when they work on it, so it sounds like new. So we called it heterogeneous. Other companies call it asymmetric, non-homogeneous, and synergistic. See if you can match the company names. What we were looking at is using a single instruction set architecture versus multiple instruction set architectures. And so then it'd be easy for the operating system to move applications from, say, a large high-power core to a small low-power core, depending on how the application was behaving. And if we had that, we'd have many benefits, both in terms of power, throughput, and mitigating Amdahl's law, which I'm going to talk at on the following slides. So Grachowski et al. From Intel in ICCD 2004 paper looked at the potential power benefits of asymmetric CMPs, further voltage scaling, more clock gating, and controlling speculation, basically predicting branches only when you have higher confidence in them and basically stalling when you don't, things like that. And they showed that asymmetric CMP had the biggest potential power reduction going forward. Obviously, there's been a lot of clock gating and it saves a lot of power already, but they figured you could get at most 2x further from the gating. And the voltage scaling runs, is spread over 18 years, where the asymmetric CMP could give you a quick fix in one generation. Amdahl's law is pretty famous. Parallel speedups are limited by the serial portions, right? So if you've got a code that's 90% parallel, well, let's say 50% parallel and a 50% serial, even if you make the 50% parallel portion infinitely fast, you're only going to speed up the program by a factor of 2, right? So, but the heterogeneous cores can kind of give you a way out of this, right? So if you think in terms of power efficiency, you can use the big core for the serial portions. So then you're only using one core. You can dump everything into that one section of code, all the power, and use many small cores for the parallel sections. Now, those are more power efficient. So overall, you can get both the kind of performance advantage from having the serial portion on the big core and more power efficiency from having all the small cores to the parallel section. So they built a discrete 4-way SMP and ran one socket at regular voltage and the 3 other at a low voltage. So this wasn't a very big test. This was basically limited by the fact that their platform only was a 4-way machine. And so, in real life, you'd have many more of these smaller cores. Like with the IBM Cell, you'd have 8 synergistic processors and 1 master processor. But even so, they achieved a 38% wall clock speedup using a fixed power budget. Okay, so conjoint core is another idea that Rakesh Kumar and Dean Tulson from UC San Diego and I have written about. And so the idea there is, ideally, you want to provide for the peak needs of any single thread without multiplying the cost of that peak need by the number of cores. So to execute a program, most of the time you don't benefit from a highly parallel microarchitecture, but sometimes you can get benefit from it. So you don't want to have basically the peak core where it's designed for all the different possible applications, their peak needs, because it's over-designed and for the average case. So the idea here is share basically resources that provide the peak performance that you need for a core, so it's not replicated. And that can give you a more efficient design. So what we showed in our micro paper was that you could get a huge core area savings, close to 50%, if you include the crossbar area in the calculation. And the slowdown for sharing things like the floating point unit, the instruction cache, the data cache, and the interconnect interface was only on the order of 10%. And that's if you're running, in this experiment, on an 8-core CPU where they were sharing in pairs. If you're only running 4 threads, there's basically almost no downside from sharing because there's no contention for the shared unit. Now, moving up to a much higher level, it's important to have optimizations at the data center level. What we're seeing now is that the power is going up dramatically. A rack of computers in data center from the 7 kilowatt range up to 30 kilowatts or more, even like 55 kilowatts. And so dealing with this is very difficult. And it's also making front page news. This was an article in the Wall Street Journal last year. And I think you've probably also seen pictures from the air taken of the Google data centers up by the Columbia River, where they can make use of the cheap electric power and the cooling and all that kind of stuff, the big cooling towers. So we've got a group working on that at HP that have done 3D modeling of data centers. And by arranging the workload in the data center, you can optimize the power. Based on what they have today, they can save 25%, and they're looking to save even more going forward. So it looks like I've got some time for this last section. Does it end at 5:15? 5:30 actually, well, I'm going to end early then. Well, that's good. We can have some questions. Yeah. Okay. So this is kind of my pet theory on the evolution of computer architecture ideas. So my conjecture is that looking back over computer design history, there's no such thing as a bad or discredited idea in computer architecture. Only one applied at the wrong level or at the wrong time. And I'm going to give some examples of those. And it fits in with the evolution idea of reusing and recycling. So the examples I have are SIMD, data flow, high-level language architectures, capabilities, and vectors. So SIMD was an efficient way of computing proposed in the late 60s, and we saw machines like the 64 processing element ILIAC-4 that was operational in 1972 at NASA. The problem with that, it was very difficult to program, and the peak performance was much higher than the sustained performance. Later on, there was research at HP by Ruby Lee and her colleagues on extensions to the PA RISC, and then Intel adopted the MMX architecture, where basically a 32-bit word is split into 4 8-bit chunks. And you can use those, for example, like RGB and alpha in graphics. So that's basically just making efficient use of a larger word size for small parallel data that is operated on in parallel. And it's primarily used in libraries or specialized code, so you don't have to worry about programming it as much. It's kind of hidden from the user. And it only has a very small increase in hardware, like 1%. So we took something that was basically unsuccessful, and we made the idea successful by implementing it in a different time, in a different context, in a different way. Now, data flow was widely researched in the late 80s as a way of building processors. And there are lots of problems. They're very complicated machines. They often came with a new programming model. But what we've seen recently in the last 10 years is we've got out-of-order execution machines like the Pentium 4 and are kind of a limited form of data flow, and like EV6 from DEC and Compact. So basically the issue queue issues instructions when the operands are ready. That's kind of a data flow kind of thing. But it keeps the same instruction set architecture. So you don't need to have a new compiler or anything like that. And it keeps the same programming model. It's still complex internally, but it's hidden from users. Okay. So what about high-level language architectures? That was a very popular research topic in the late 70s and early 1980s. There was kind of a rallying cry, closing the semantic gap, that programming languages, dealt with these, at then, which seemed like really high-level things like Fortran. And the computers were executing all these bit streams, and so there was this semantic gap between them. And there were a few attempts, actually it goes back to the early 70s, to implement higher level stuff in hardware, like the snowball machine, Symbol. But it didn't work out very well. The machines ended up being slow. But nowadays we have Java interpreted in software, just-in-time compilation. It gives us portability, and the performance loss that we see doesn't matter for some applications, and it's a key enabler in many things. So capabilities, again, dredging out history, were a popular research topic in the 70s, and the Intel 432 of the Orkin group implemented capabilities in hardware. So for every memory reference, it was tagged with what it could do. The problem here is it had very poor performance, and there had been a lot of research into capabilities, but when the 432 wasn't successful, it kind of killed the field. But nowadays, security is increasingly important, and capabilities at a file system level combined with standard memory protection models provide much less overhead, but can give you a lot of this functionality. Another way of getting capability like features is having virtual machine support, where you're not actually running on the machine, or you don't have the full privileges. And virtual machine support is, again, one of these ideas that was very popular kind of early on, kind of stagnated for a while, and now seems to be really taking off.
Can you define exactly what capability is?
Yeah, capability is, you have some descriptor which says what kind of memory you can reference. That was the way it was implemented, like in the 432. And so you'd have to first, in order to do a memory reference, then you have to look up the descriptor and figure out, it's more complicated than standard address protection. Okay, so just some ideas, lessons from my idea evolution theory is don't be afraid to look at past ideas that didn't work out, because they might be a good source of inspiration. And some ideas that didn't work out in the past might be successful if reinterpreted at a different level, place, or time, when they can be made more evolutionary than revolutionary. Okay, so in conclusion, the Powerwall is here. It's the wall to worry about. And you have to think, basically, when you're making trade-offs in the system design, you have to keep that foremost in your mind. And it has dramatic implications for the industry, from the transistor all the way through the data center. We need to reclaim past efficiencies and scale back microarchitectural complexity to get more efficient cores. And I believe that this Powerwall will usher in a golden age of parallel programming. Now, this isn't to say that there's not a lot of open research to do, both in architecture and especially in programming. But we may want to look at some previously discarded architecture ideas to give us inspiration in our current predicaments. Okay. Thanks for your attention. That's the end of my talk.
Now is we'll stay online and take questions.
Okay. Don't all raise your hands at once, yeah? Yeah.
Exactly what contributions do you see the parallel processing making through the Powerwall?
Well, basically, the idea is, we've been seeing with the dual core designs and the quad core designs, instead of making the core ever more complicated, which has got the low efficiency, you want to move back, along that curve and make each core more efficient. So you have to be reasonably effective in your parallelization, right? So I kind of glossed over it earlier. If you're only getting a 2x speed up from 4 cores, then, if you powered, if you're using all 4 cores, but, only getting a 2x speed up, then you're wasting some leakage power there and perhaps dynamic power. So it's actually a very complicated problem. But hopefully you'll get power efficiency there by having the simpler cores.
Quantitatively, it can be a significant improvement in your mind.
Right. Right. By a factor of like 4 or 6. Yeah.
You sort of alluded to this a little bit, but how do you see sort of the recent resurgence of virtual machines affecting computer architecture evolution, or other way around?
Yeah, so I guess I should repeat the question. So what do I see about the current research in virtual machines? Well, I think there's a lot of good things happening now with both major microprocessor vendors, AMD and Intel, about adding support for virtual machines into their architecture. IBM had it, way early on with 360, but and we're seeing it in stages. So, initially it's just fixing the problems where you have privilege-sensitive instructions, which act differently if you're running in privilege mode or not, and it cause troubles with virtualization. So they're fixing the basic kind of things, and we're going to see a second wave. AMD's already announced this, where they add support for virtual I/O and having I/O memory management units, I/O MMU, things like that. AMD's also talked about additional support for virtualization of virtual memory with page table support, things like that. So I think there's a lot of really exciting things that can happen at a system level when virtual machines are ubiquitous. Now, we might not have them ubiquitous in all situations. So if you're going to be running, some giant scientific simulation, you probably won't want a virtual machine. They don't even like having operating systems in the way practically on those machines because of the operating system noise and various other problems. So, but I think for the majority of users, it opens up a lot of potential benefits. Yeah?
Well, I don't see you saying much about how these interconnects for parallelism are actually supposed to work. I mean, we have, historically, 2 things have worked. Shared memory multiprocessors and fairly loosely coupled clusters, and everything in between has been a commercial disaster.
Right.
And we're about to find out if that's going to be true for the PlayStation 3 and it'll take down Sony. The feeling in the games community seems to be that it may be possible to program the thing, but it's going to cost you an extra year or 2 time to market.
Mm-hmm.
And I realize you can build the hardware, but it looks like build it and they will come. How do you make something programmable? I mean, is something that people can actually stand to program?
Right. Well, I won't exactly repeat the question because I think it'll be obvious in the answer. But I think your point of having the 2 successful models being the cluster computation and the shared memory multiprocessor, I'm hoping that we can limit it to just that. And it may be that the other things wouldn't work anyway. But that makes it simpler to program if you only have to deal with 2 levels of abstraction. So for example, for the cluster-based computing, you can have MPI to communicate between clusters. Shared memory, there's a bunch of things, OpenMP, things like that. So what I want to avoid is having, various levels, like having, somewhat shared, memory that's shared but far away, all these kinds of things. So hopefully if we have all the cores on one chip and we have more of a dance hall architecture and we have fast interconnects between, maybe you have 4 sockets on a blade in a coherency domain, we can kind of keep it more or less to those 2 levels for programmers, because that's already complex enough. So that answer your question?
Well, I thought you were proposing more things, like a return to hypercubes, or the BBM butterfly, or machines with big interconnect architectures, or InfiniBand, or...
Well, if you look at what's been happening in the industry, there is now a push towards lower latency Ethernet switches. For example, there's a couple of vendors, Fujitsu and Fulcrum, which have very low latency switch chips. There's a push towards higher radix switch chips. Fujitsu went from 12-port, the Fulcrum's 24-port. The Cray Widow, Black Widow, which was recently announced, is like a 64 radix. Bill Daly was consultant on that. So, there's work on reducing the interconnect latency and being able to span larger connections of machines. But hopefully we can just keep it down to kind of that cluster computation with things like MPI, RDMA, things like that, and the shared memory, that we don't have to introduce kind of a third model for programmers to worry about, because dealing with 2 models is already very taxing. Yeah?
The last I saw, Intel was talking about on their 4-core chip having pairs of cores share L2s, so there'd be 2 L2 caches for the 4 cores. So this is moving a little bit in the direction that you're not enthusiastic about it. I'm not particularly enthusiastic about either.
Right. So it's a question of how much is that noticeable by the programmer or not. I mean, I think for
explosion in different architectures.
Yeah, basically if you have a 4-core machine, I guess I'll repeat the question, having an L2 cache shared between pairs of cores. I mean, sharing is good for a lot of reasons, and it's hard to build completely flat structures. I mean, the Niagara has 8 cores with a crossbar, but that's kind of the most you can do, I think. So, yeah, but as long as it's not something where it's big enough where the programmer will have to start thinking about it. Okay? Yeah.
I have a question about the HP lab in general. So, how close are you to a product, or is this very fundamental research, what you're doing in the lab, architecture lab?
Well, we actually have a range of things going on. So we have some things we're actually working with customers on parallelizing their problems, and we have some stuff that's very far out, like 5 to 10 years that we're looking at. So it's called a portfolio. There's a lot of emphasis on good management and all that kind of stuff. So you want a portfolio of research products with different durations. Just like your bond, portfolio, different durations and bond fund, right? So, yeah.
So my question is about the HP lab as well. I was wondering if you're looking into any alternate forms of computing, like quantum computing or anything like that. It seems like you're getting marginal returns on with increasing complexity.
Yeah, there is a group called Quantum Science Research at HP Labs, and they're looking at things that are very far out. So they're looking at nanotechnology. There are some people doing some quantum theory kind of things, but it's not a huge effort. It's again fits in with the whole portfolio idea. Okay. Well, thank you very much for your attention.
For information on other online Stanford seminars and courses, please visit study.stanford.edu.
The preceding program is copyrighted by Stanford University. Please visit us at stanford.edu.